Homework 2. In question 1, it asks you to write the rate law expression based on the experimental data. The rate law is a mathematical equation of reaction rate as a function of concentration. In this case, because it's a gas phase reaction, so it's also a function of partial pressure. In order to write the rate law, we need to find the K constant, the rate order, alpha, and the beta. These are the three parameters we need to find out. There are many ways to do it, but the easiest way is to keep one pressure constant and change the other. Okay, so for example, if we choose run number 1, number 2, the hydrogen partial pressure are the same, and therefore this partial pressure does not affect the reaction rate. We can combine all these together, and therefore the reaction rate can be written as a constant times the only thing changed is the partial pressure of nitrogen and the beta. So from number 2 to number 1, the partial pressure of nitrogen increased almost twice. And if the reaction rate of number 2 is C times PNO to the beta's power, then V1 is C times twice PNO to the beta's power, because the pressure increased twice. Okay, and that will give you C times 2 to the beta's power PNO beta. Okay, so you can also move this out, 2 beta times C PNO B beta, and this is just the rate for the run number 2, so V2. So V1, the first run reaction rate, should equal to the reaction rate for the second run, but times 2 to the beta's power. Okay, let's look at the experiment. How much increase? So from 0.033 goes to 0.137, that's about 4 times. And that means 2 to the beta's power should equal to 4, and beta must be 2. Okay, so for nitrogen oxide, it's a second order reaction. We keep hydrogen constant. We find out nitrogen oxide is a second order reaction. Okay, now let's do the same thing for hydrogen. Okay, so here this shows you how we find out the beta is 2. Similarly, in order to find the alpha, we choose number 3 and number 4. Okay, so number 3, number 4, you can see here the NO, nitrogen oxide pressure, is the same, and therefore it does not affect reaction rate. The only thing changes is hydrogen, and for hydrogen it goes also from 4 to 3, it increased twice, and the reaction rate also increased twice. Okay, also increased twice. So that means that just like we did before, it should be 2 to the alpha's power equals 2, and therefore alpha must be 1. So first order reaction. For the first order reaction, if you increase pressure twice, the reaction rate also increases twice. For the second order reaction, when you increase pressure twice, the reaction rate increases 4 times. And therefore, the rate law should be written as a constant times partial pressure of hydrogen to the first power, nitrogen oxide partial pressure to the second order. Now we need to find this constant, rate constant. To find the rate constant, we can choose any of these run. For example, number 1. Okay, the reaction rate is given, so this reaction rate is 0.137, and that's here. Okay, and the partial pressure of hydrogen is 53.3. It's this one. So here is 53.3, and the NO partial pressure is 40. So here is 40. Okay, 40 square, 53.3 square, n times a constant rate constant. This equals to 0.137, and we can calculate the K constant. Okay, so K constant can be calculated. You can choose run 2, run 3, or you can average 4 of them. Okay, and so the final solution should be 1.6 times 10 to the minus 6, that's the rate constant, times hydrogen first order, NO second order. In question number 2, you are asked to derive integral rate law for the zero order reaction. Okay, the method is similar as we derive the first order and the second order reaction. First, we write rate law. For the zero order reaction, the rate law is reaction rate equals a constant K. Now to integrate this equation, we need to write definition of V as a derivative of negative dA dt. That's the change of concentration over time. That's the definition of reaction rate. And therefore, we have this differential equation. So the left side is the derivative of A over T, right side is K. In order to integrate this one, we have to separate the variables so that one side only have concentration of A, the other side only have time. To do that, we times dt in both sides. Okay, and therefore the left side only have dA, the right side only have dt. And now we can integrate. Okay, integrate. Note that we integrate from initial concentration of A to final time from 0 to T. Okay, so we know that integration dx with constant 1 is just x, and therefore the left side is just the concentration of A. All right, the right side is also constant times dt. So a constant times dx integration is just constant times x. So the right side should be negative kt. All right, but don't forget it's from initial concentration to the final concentration. Here from 0 to t. Okay, and the final minus initial, and that's what you get. The final concentration minus initial concentration equals negative kT. That's integral rate law for the zero order reaction. Using this equation, we can calculate the half-life. Okay, so using this equation, the time for a concentration is negative K A minus initial. Okay, so we calculate how much time you need to consume concentration to a certain value. Okay, now for half-life, this will goes to half initial concentration, and therefore the time should equals to K. Here is half A initial concentration minus A, and that give you, okay, half A minus A should be negative half initial concentration, and the negative cancel, so you have 2K A naught. Okay, so you see the half-life for a zero order reaction is proportional to the initial concentration. That's very different from first order reaction, in which the half-life is independent of initial concentration. In question number 3, it tells you a certain reaction is first order, and the time is 540 seconds, and the concentration changes to 32.5% of initial concentration. So whenever we talk about the time and the concentration, we should use integral rate law. Okay, integral rate law is about concentration as a function of time. And therefore, for the first order reaction, we know the natural log ln A over A naught is proportional to time. Okay, so that's the equation. All right, that's the first order reaction, integral rate law. In question A, what is rate constant? So we ask you to calculate the rate constant. All right, so change this equation, both sides divided by negative t. All right, so Ka can be calculated. You need a ratio of concentration A over A naught. All right, because it says 32% remains, that means this is 0.33325. Okay, and then divide by A naught, they cancel each other. So you get negative log 0.325. All right, so that's Ka. In B, at what time after initiation of the reaction there will be 10%. So again, this is about the time and the concentration. So so again, the same equation. We want to calculate the time, so we divide by negative K on both sides, and that gives you this equation. Okay, to allow you to calculate the time. Again, you need this ratio, concentration over initial concentration. It says 10% remain. That means this is 0.1 A naught. Okay, so A naught cancel, and that gives you negative ln 0.1 divided by K. And the time is 1106 seconds. Question number 4. It gives you a first order reaction, the rate constant, and they ask you to calculate the half-life. Note that N2O5 have a coefficient 2. Now in class, we derive first order reaction A goes to P, we'll assume the coefficients are all 1. But here you have a 2. So whenever you have a coefficient 2 in front of this A, okay, then the reaction rate for A should be twice as fast as P and twice as fast as the reaction rate of reaction. Okay, and therefore the equation we derived in class for the integral rate law for first order reaction are all valid. The only thing you need to change is the K. So for Ka, we say this is effective rate constant, should be twice of the rate constant of reaction. And therefore, that's all you need to do. So here, all right, the first order reaction, the half-life, we already know it's ln 2 divided by K, but here has to be 2K. So Ka is effective K constant. It must be times 2 of this K constant. Okay, and therefore you can calculate the ln 2 divided by 2 times 3.38. Okay, that's half-life. Next, what will be the partial pressure of N2O5? Initially 32. So this is A naught or P naught. It asks you what is the P. Okay, when the time is, let's say, 10 seconds. So you know the time you want to calculate the partial pressure at this time. Again, that's the integral rate law. So it's natural log or exponential. Remember, these are different ways to write. So that's the concentration, all right, as a function of time, or partial pressure as a function of time. But remember, the K must be, here is effective K, so it's twice of this K, all right, of the reaction rate constant. Okay, so for A, the time here is 10 seconds. Okay, so initial constant or pressure times e to the negative 2, note that 2k times t. Okay, that gives you 32 kilopascal. Now when the time goes 30 minutes, then you have to change to seconds. Okay, so 30 times 60, that gives you seconds. All right, and that gives you 28 kilopascal.